All right. Happy Friday. We made it. So, kind of a thin crowd. Y'all are the faithful ones. Thank you for coming.
Yeah, me too.
What's that?
Yeah.
All right, I'll put it on there. I don't know how I can do that. It's not in the syllabus, but I'll put a big star on this page to say these were the folks that showed up on Friday. Yeah, and so you'll be in my book, my mental book. It's good.
God
Yeah,
bless.
yeah. So yeah, Fridays. This is all right. I don't ever look at the room and see a lot of people missing and say the biggest insult you can say to people who got up and showed up, that no one's here. You ever hear that? You show up, you're there, and there's a lot of people missing, and they're like, golly, nobody's here. Like, what am I, chopped liver? I mean, I'm here, right? Yeah, so
in Zola's class, only 7 people had showed up
Mhm.
for like a Friday lecture. And
Mhm.
it was like, wow.
yeah. All right, so we're going to talk about equilibrium today and Le Chatelier's principle. We kind of hinted at it last time, but we're going to get into how systems of equilibrium respond to pressure. Not just pressure like external pressure, but stresses on equilibrium. And this is the idea of equilibrium. It looks like there's nothing changing because the concentrations are the same, but there's constant collisions and transformations from products to reactants. And so a great macroscopic view of that would be jugglers, where they in general have the same number of clubs in their hand at all times. So that's the unchanging part. But the equilibrium is really illustrated by them passing the batons back and forth to each other, or clubs in this case. And so that's a great illustration of equilibrium. It's constantly going, but you can't really detect any change. And so this is Le Chatelier's principle. If a system is at equilibrium and it's disturbed by changes, so this disturbed piece is really important. We call that stress. If you stress the system, how will it respond? And so you could stress it by changing the temperature. You could stress it by changing the pressure or the concentration. It would be like these jugglers have an equilibrium with the little clubs, and you throw a couple more clubs in on one side. Now this person has 4 in their hands instead of 2, and they're going to pitch a little faster until they reestablish the equilibrium where they both have 2 in their hands. So you put a stress on it, and it responded by putting more into play. So we see that, and we're going to go through several ways of stressing the equilibrium here this morning. So what does it mean to shift its equilibrium position? A lot of times we look at a reaction and we say, what's the position of the reactants and products? Do we have more reactants or do we have more products? And so it's sort of shifting its position. You take the stress and then you move that stress through the reaction. And so let's look at that, what we mean by equilibrium position. Here's a good example. You have a carbonated drink. There's a lot of CO2 dissolved in the liquid, and the pressure above that liquid is around 3 atmospheres, so 45 psi. Not huge, but also not nothing. Right? You open the lid, you hear that psh, that's the release of the pressure, and then you see the bubbles form. Equilibrium is starting to be shifted. You've removed the gas phase CO2, or the pressure, and now it's coming out of solution and moving to the gas phase to counteract that change. So if you drop the pressure, then more CO2 forms in the liquid and rises to the top to go against what you just did. It's trying to put pressure back into the atmosphere above the liquid. So there's lots of shifts going on just when you open a Coke bottle. So here's a reaction. Let's think about this reaction being at equilibrium. And what does it mean to press on something? Well, it'd be like adding more. So adding more hydrogen or adding more nitrogen, we talk about that as pressing on the reactants. We're pushing on it because we're adding more of that. And how will the equilibrium respond? It will respond by shifting to the right. So if I add more hydrogen, it's going to produce more ammonia. If I add more nitrogen, it's going to produce more ammonia. Here's a clue, you don't have to add both. All you have to do is just push on one. If I just add hydrogen, there's more hydrogen to find the nitrogen. And that more hydrogen will find more nitrogen and make more ammonia. So you don't have to push on both of them. You could just push on one, and it will shift this equilibrium to the right. You can also pull on a reaction. So if we take this gas phase reaction and we run this through cold temperature and we turn this to a liquid, we've pulled it out of the gas phase, and we can sort of collect that over here. And so this was going to cause the equilibrium to shift to the right. So taking a product away, or even taking a reactant away, will pull on the reaction. So pressing is adding more of something. Pulling is like pulling on a reactant. You're removing it from the system. So if we remove ammonia by making it a liquid, then we'll pull this reaction to the right, and we'll make more ammonia to replace the amount that was missing. But does it make sense to you? It seems, I see lots of nods. Okay, so there's nothing magical about Le Chatelier's principle. It's just common sense based upon these reactions. What if we add more products? So we stuff ammonia in the system, we can actually run this reaction backwards. And so then the equilibrium will shift to the left and we'll get more reactants. So it's at equilibrium first, then all of a sudden our cooling system stops and our liquid ammonia re-evaporates, and now we have more ammonia. It's not at equilibrium anymore, so then it's going to shift backwards until it's at equilibrium again. So we'll actually go backwards, we'll make more nitrogen and more hydrogen. We could also pull on the reactants and move the reaction backwards. So if we had this system at equilibrium and we remove the hydrogen, remove the nitrogen, then the equilibrium will shift. It says to the right, it should say to the left. That's a typo. Oops. Okay. Make sure that's still going. Yeah. Okay. And so we're going to talk about this reaction quite a bit because there's a lot of moving parts. We have a single reactant in nitrogen. We have 3 moles of hydrogen, so there's a 1-to-3 ratio there. Produces 2 moles of ammonia. So this is a great reaction to study because it's got a lot of different coefficients. It's also still pretty simple. It's only 3 things. There's 2 reactants and a single product. So this is a great reaction to think about. It's also a very important reaction for us as a society because we used to have to get our fertilizer from manure, either cattle manure, or a really important source of fertilizer was bat guano. It still is. A lot of nitrogen, ammonia, urea, urine from bats in caves, and it's a very rich, very rich fertilizer. You can extract the nitrogen compounds out of there and the phosphorus compounds. And then during World War I, there was a blockade, not letting the German and Axis powers have access to the nitrates from fertilizer and so on, so that they couldn't make bombs and dynamite and weapons and that kind of thing. And so then they had to come up with their own way to make nitrates, and ammonia is one of them. And so they were able to make nitrate for gunpowder and gun cotton using this process of nitrogen and hydrogen to make ammonia, because you don't require any shipments. You can get nitrogen out of the atmosphere. You can electrolyze water and make hydrogen. And so this was a way that the Axis powers were able to get around the blockade on nitrogen-containing compounds. And Fritz Haber used Le Chatelier's principle to make this ammonia. He also extended his chemistry work to make chemical weapons, and so he's kind of a controversial figure. He made nerve agents and so on, and so not a great guy. Here's the Haber process, this industrial process, and you can see several things in this process that you as a Gen Chem 2 student can understand, okay? But back in the early 1900s, this was Nobel Prize winning science, and now it's in the second semester course. So it kind of shows you the march of science. The things that were revolutionary just 100 years ago are now in the second semester of chemistry. So chemistry gets more difficult as time goes by, as you can attest to, I'm sure. Okay, so what do we have here? We have a catalyst. All right, so here's a catalyst to help get the nitrogen and hydrogen to react together. So what does that do? It just changes the reaction rates. It doesn't change the equilibrium, but it lets equilibrium be achieved faster. And so it makes the reaction rate go faster. So we have hydrogen and nitrogen coming here to react with this catalyst. It's also got a heater, so it heats it up to increase the reaction rates. These heat exchangers are just temperature control, okay? And so then they have ammonia and nitrogen and hydrogen going through this, again, another heat exchanger. And then they come over here, and this is Le Chatelier's principle, this refrigeration loop. Because see here, here's ammonia liquid. And so we're pulling on the products by pulling that out of the gas phase. And so this is, and then you just put a little tap here underneath the level of liquid, and you can pull out the liquid ammonia and remove it from the system. And then this condenser is not cold enough to condense the nitrogen and hydrogen. Those have a really, really low boiling point. And so they pass through that cold condenser. The ammonia drips out, but the nitrogen and hydrogen go back over to the catalyst and make more ammonia. And so we're pulling on the products constantly and driving this reaction forward. And so it becomes a stable process where you feed in the hydrogen and the nitrogen at a certain rate, and that matches the rate at which the ammonia comes out. And this was the Fritz Haber process for making ammonia. And so we just like to emphasize that, not because we like Fritz Haber, but because we like Le Chatelier's principle. Okay. To show you how big and industrial this is, I was in Karlsruhe University at a meeting in Germany. I've only been to Germany twice, but it just happened to be there in Karlsruhe, and there was a university there, and I'm walking around campus because I thought, what's the German university look like? You know, and it's a Saturday, so nobody was around. But I saw this big steel thing standing in the, I went up and looked at the plaque, and it said that was the catalyst chamber for the Haber process. There it is. I mean, like that was the actual physical chamber that they used in the wartime effort. And look how big it is. This is a bolt on the bottom of that, and that's my hand. So that's the size of a bolt. You know, it was that big. So just big industry. I saw that and I thought, oh man, I got to get a picture of my hand next to that bolt to show my students how big it is. Okay. So this was in a big, huge, industrial facility making ammonia. So this is a sort of an illustration of the Le Chatelier principle. Here you have the equilibrium concentrations, and then if you add in the hydrogen at a faster rate, you disturb the equilibrium. So you see this is a perturbation, and now it's no longer at equilibrium. You've put a burst of hydrogen in, and then achieved a new equilibrium. So this is after you add in hydrogen at a higher amount, you get a new equilibrium. And look at that, the ammonia went up. And so we have a higher amount of ammonia than we had before. And we just added one extra reactant. We just added extra hydrogen, and that produced extra ammonia. And you see the nitrogen drop down because now we have more hydrogen in the system to go find that nitrogen. And it found it and used it to make ammonia. So that's what we did. We pressed on that hydrogen, and the equilibrium shifted to the right. And so this is the area that we're talking about with Le Chatelier's principle. It's this area right here. We had a system at equilibrium. We put a stress on that system, so it's no longer at equilibrium, and it achieves a new equilibrium, and the ammonia increased, right? So it went up. That's how it relieved that stress. It took in the extra hydrogen. We saw that nitrogen was reduced, and ammonia was increased. And so that's Le Chatelier's principle in pictorial form. There's some other effects. Here's an example of an endothermic reaction. It's a kind of neat reaction, actually, because it's the color depends upon the temperature. And that's kind of cool. I mean, we've seen that nowadays. This was much more cool before we had these shirts that change color in the sun, or had thermometers on fish tanks that you could see the color change with temperature. But, still, it's a neat effect. We have this cobalt chloride. It's a tetrahedral structure on the left, and then when you change the temperature, it swaps out the chlorine for water molecules and makes a pink structure and cobalt hexahydrate. And it's an endothermic reaction. So you can think of this delta H of reaction being positive as at this point of the arrow, you have to have 100 kilojoules to move to the right. If you move to the left, you get 100 kilojoules out. So whenever we write the delta H of reaction, we write it in the forward direction. Okay, and you have to add this amount if it's positive when you cross the arrow. Does that make sense? So if I raise the temperature of this reaction, I have more joules, so this is going to push it to the right because it's an endothermic reaction. If I add more temperature, then that temperature is going to go into the reaction and shift the equilibrium to the right. What if it's an exothermic reaction? It'll go backwards. So you think about that. If it's exothermic, this reaction is trying to put heat into the environment. If I raise the temperature of the environment, that's harder to do. And so it'll stay on the reactant side. It'll move backwards if it's in situ when you raise the temperature. If an exothermic reaction will move backwards. And so that's what I have over here. Increasing the temperature pushes an endothermic reaction forward, and increasing the temperature pushes an exothermic reaction backwards. Okay, if we have a catalyst, remember what a catalyst does. It reduces this this activation energy. So right here, this would be with the catalyst, E cat, and then this one is E no cat. It does not change this. No delta H change. Or delta G or any of the other deltas. And so the equilibrium position is based upon the energies of the products and the reactants. It's not based upon the activation energy. This is a kinetic effect. So kinetics, okay, is this piece in the middle. That's kinetics. Okay. This piece right here is thermodynamics or equilibrium. And we cover that in the chemistry course called thermodynamics. So PChem 2 is thermodynamics, and we get into what makes this equilibrium constant what it is. We can actually solve for the equilibrium constant if we know everything about the products and the reactants. So the catalyst doesn't change the equilibrium constant, but it allows equilibrium to be achieved faster. So now let's get into some calculations. The next several lectures are going to be really calculation heavy. And so I'll go slow. You can do the calculations in your notes. Be sure to ask questions about every little detail. If by chance you're not here today and you're watching the video, pull out your pen and actually do the calculations with the video. And if you're reviewing, do the calculations with the video, okay? If you're not sort of calculating with your pen in your hand and a piece of paper, you're really not engaging the mind. And it's a false comfort to watch videos because, you know, you hear sciencey things, but you're really not engaging the mind unless it goes in your eyes, bounces around in your brain and out your hand. Even if you're just sort of copying down the equations that I'm using, if you redo those calculations, pause the video, make sure you understand where the units cancel, why I chose this constant and so on. That's really how you learn from the videos. Just watching the video really doesn't cause it to stick. It's got to go through your whole body and then it'll really stick. That's the way you learn a new thing using the videos. Okay, so we have several types of calculations. We could take equilibrium concentrations and calculate the equilibrium constant. So if you're looking at a problem and it gives you the equilibrium concentrations, that's one of the things that you can do. Sometimes you have the equilibrium constant, and you've got other pieces of the puzzle, but you're missing one of the equilibrium concentrations. Well, again, you've got one equation and one unknown, so you can solve for that one piece that's missing. Sometimes you can calculate the concentrations from initial concentrations using the equilibrium constant expression. So we'll go through all of these different types of calculations. So if we have the situation where we have the equilibrium constant for the formation of ammonia is 0.06, or 6 times 10 to the minus 2, and here's our reaction. If the partial pressures of ammonia and hydrogen are 1 atmosphere, what's the partial pressure of ammonia? So we're starting with the reactants, and we know the equilibrium constant. What's the pressure of the products? So this is when we get back to those ice tables. And we can do this one directly using the equilibrium constant expression. If we look at this reaction, we know the partial pressure of ammonia is going to be squared right here. So it's products over reactants. And then we know the reactants in the bottom, the hydrogen is going to be cubed. That's probably the number one place where people mess these up, is they get their exponents wrong. And so we have this equation, and this Kp is our equilibrium constant. So we put that in there. And we know 2 out of the 3 variables. It says the partial pressures of nitrogen and hydrogen are 1 atmosphere. So those go down here in the denominator. And it's asking for the partial pressure of ammonia. So we don't even need a table for this one. We just need to know the equilibrium constant expression. So we can rearrange this. Let's move these over to the right and take the square root. So we move those over, take the square root. 1 atmosphere cubed is 1 times 1, so we end up with the square root of 6 times 10 to the minus 2. So here's the partial pressure of ammonia in this situation will be 0.245 atmospheres. Not a lot, right? We start with 1 atmosphere of our reactants, and we only have 1/4 of an atmosphere of ammonia. And that's why we needed this catalyst, right? So we needed that to happen quickly, and we needed to pull on the products. So Haber said, let's liquefy that ammonia and pull out that amount, make that partial pressure drop, and so this reaction will go forward at a faster rate and more completely. So let's illustrate the Le Chatelier's principle by doubling the concentration of the hydrogen. So same equilibrium constant, same reaction. If the hydrogen pressure was doubled to 2 atmospheres, what does this do to the partial pressure of ammonia? Before you even start the problem, just think about it and say, hey, we're doubling the concentration of one of the reactants, so the product ought to go up. So if you do this problem and you end up with the product being less than it was before, you know you've done something wrong. So always try to engage your brain cells. Don't just follow the procedure of the math. Here's the same equation. Now we have a 2 in the denominator for the hydrogen concentration. So it's going to be 2 cubed, or 8. Solve for it with the square root. So now we have the square root of 8 times 6 times 10 to the minus 2. And that's 0.693. So it went up quite a bit, actually. Yes?
So we're just assuming that the oxygen is still 1, even though it's stated.
Yeah, it's not stated, so we'll just say we doubled the hydrogen. So we're just sort of coupling this with the previous calculation.
Is that all it does?
Yeah, that's all we did. Yeah. And so it's always good when we have a change like this to see what percentage was the change, right? So I put a little sticky note here. The pressure of ammonia increased by this ratio. It was 0.245, and now it's 0.695. Let's just take that ratio and see what it does. It's 2.8. 1 would have been 100%. This is 2.8, so it went up by 280%. So that's pretty good. We doubled the hydrogen, which would be a 200% increase in the hydrogen, and we had a 280% increase in the ammonia because it's hydrogen cubed, right? It has a huge effect. If we'd have doubled the nitrogen, it wouldn't have gone up that much, but we doubled the one that was cubed. And so it's really a huge dependence upon the partial pressure of hydrogen, that equilibrium. And so you could look at this equation and say which one has the most effect on equilibrium, and it would be the hydrogen because it's cubed. We're going pretty fast, so we're going to finish early. So if you have any questions, you're bashful, you want to ask, make sure you ask them because we've got time. Okay. Yes.
So if we're doing like the reverse reaction, they flip, right? Products.
Yes. Okay. So if we wanted to write this in reverse, so let's say we had the destruction of ammonia. I'm going to leave the G's off because they're all gas. Is that correct? Okay. So we have some room. Okay. I've got the reverse reaction. That's going to be, I'll call it K prime, right? Is equal to 1 over K. So we would just take 1 over this number, and that would be the equilibrium constant for it. Okay, so it would equal 1 over 6 times 10 to the minus 2 for that equilibrium. And you can tell that, I'm just going to go ahead and write this out. We'll say K prime is equal to products over reactants. So we have the pressure of N2 times the pressure of H2 cubed divided by the pressure of NH3 squared. And you see how that's the inverse of this? Yeah, so if you reverse the reaction, you invert K. And that's on the homework, I think. That's one of the ones on the homework, is that we write the reverse reaction. What do we do to K to get the new equilibrium constant for the reverse reaction? And it's 1 over K. I believe that's a homework. I don't know. And then again, you would put in the numbers and so on. You could do the same problem and you'd get the same results. Okay, so now let's this is an example from the OpenStax book. If a solution with iodide and iodide concentrations of 1.01 molar came to equilibrium, what's the equilibrium constant expression? Okay, so we're just asking for the expression. So this is a term for you here, the equilibrium constant expression. We don't have enough information in this problem to solve for the equilibrium constant, but we can write out the equilibrium constant expression, algebraically what it looks like. Do you follow me? So the expression is just the algebra. Okay. So the algebraic equation is the equilibrium constant expression. So we have at equilibrium, we started with these initial amounts. Minus X would be the equilibrium constant, equilibrium concentration. Notice we have, this is the middle of that mass action table. And before I called it initial chemical units, the change or chemical reaction, and the ending chemical units when we were doing stoichiometry. But now the E stands for equilibrium. So we let this come to equilibrium, and we have a sort of an external equation, the equilibrium constant expression, which describes what comes up on that row. Also, we have here what 0.001 molar minus X, so that's what it would be at equilibrium. And then we have 0 plus X, so we'd have X. So writing out the equilibrium constant expression, this is what it looks like in terms of concentrations, but then we just take all of these pieces here and put them in the appropriate places. So this X goes right there, and this piece right here goes, right there, and so on. And so that's what we mean by the equilibrium constant expression. And then we can simplify it. So we look in the denominator, we see two of the same things multiplied by each other, so we could simplify it like that. And so that's the equilibrium constant expression written in terms of X. Very important slide. So if there's anything you want to clarify, this is a good time.
Are we always going to get the molar?
Sometimes it's partial pressure, okay, like in the previous problem. So it could be partial pressures, but most of the time it's molarity. Yeah. So we're dealing with changes in concentration, especially when we get to acid-base concentrations. And so we're dealing with the molarity of hydronium ion, or molarity of hydroxide ion, or molarity of the parent acid. And that's what's coming up next. So we'll do generic equilibrium right now. Like this isn't acid-base, this is just ions in solution. Then we're going to get into what's an acid, what's a base, and then we'll do equilibrium with acids and bases. And then we'll pull back the solubility rules, and we'll actually look at the solubility of insoluble substances. So things that are not very soluble in water, we'll be able to use equilibrium to see how much of that insoluble thing does break apart and end up in water.
So it's always going to be products over reactants.
Yes.
Okay. So let's say that it's 2 I3.
Mm-hmm.
Would that be 2x?
Yeah, so if it was up here, if it was 2 here, yeah, then that 2 would come down here in the 2x, okay? And then it would also be, over here, it would be squared. So in this expression, I realize it's not related to this problem, but you would have right here, it would be the 2x inside and squared. So the 2 shows up in 2 places. It's 2x because I have 2 of these. This would be a 2x, so this would be a 2x. So that's the concentration. That goes inside the parentheses. And then when I make up the equilibrium constant expression, it's the concentration squared. And so it shows up here. So that 2 shows up in 2 places. It shows up in the change row as you come down. And when you write out the expression, it shows as an exponent.
So if it's 3, it's the same thing, 3x to the cube.
Yes,
Okay.
yes. Mm-hmm. So that's a good question. I'm glad that you asked that so I could point that out. Because a lot of times people are confused. They're like, is it both? Is it both 2x and squared? And the answer is yes. Yeah. Great. Okay, let's add a little piece of information to this problem. We'll say if the equilibrium concentration of I2, so look at this very carefully. This says equilibrium concentration. Okay, so that's this one down here, not the original, right? This is the initial concentration. This is the equilibrium row. And so we're saying if the equilibrium concentration of I2 is this number, then what is the equilibrium constant? That's all I need is just one of these to solve for x. And once I get x, it's x for the whole table. We learned that from the stoichiometry use of this table. So all I've got to do is just set this piece down here. Oops, I went backwards. Set this piece down here equal to 6.61 times 10 to the minus 4. See, it's saying that the equilibrium concentration, so this piece right here, is equal to this number. And now I can solve for x. Once I get x, I've got the whole thing. So x is equal to 3.39 times 10 to the minus 4. And now I can put that into my equilibrium constant expression. So that goes up on top where I had an x. And then I know if this is 6.61 times 10 to the minus 4, this is the same because we started out with the same amounts. And so you see how this one equals that one. So I could just put it down here twice, you know, and I end up doing the math and I get 776. Okay. I could put my molarities in here too. There is one thing that always made me uncomfortable with the equilibrium constant expressions. They're actually unitless. Even though it looks like I have a molarity on top and 2 molarities on bottom, so it looks like it should have the units of inverse molar, okay? They're actually, we're not showing all of this because it would just make it unnecessarily complicated. But we're really dividing all of these by a standard state of 1 molar. So every one of these is divided by a standard state of 1 molar concentration. So when we put them in the equilibrium constant expression, all the units disappear. Okay? But that would confuse the heck out of everybody if all of our concentrations were written divided by 1 molar, or in terms of pressures divided by 1 atmosphere. So that would be the standard state for the pressures would be the partial pressure divided by the standard pressure of 1 atmosphere. But in avoiding that confusion, we could possibly enter other confusions like why are the units disappearing? But that's why the units are disappearing, is that we're dividing by standard states. And so it's just 776 is the equilibrium constant for this reaction. There's no units on it. Okay. Let's try a different one. So now let's calculate the missing equilibrium concentration. So new problem, nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. This happens inside your automobile cylinders. The 2000 degrees Celsius, the value of K for this reaction is here. So we've been given the concentration, equilibrium constant here. So 4.1 times 10 to the minus 4. So that's K. Now we know the number of that. Calculate the equilibrium concentration of nitric oxide in air at 1 atmosphere pressure and 2000 C. And so the equilibrium concentrations of nitrogen and oxygen at this pressure and temperature are here and here respectively. That just means that they're in order. So nitrogen is the first one, oxygen is the second one. So let's write out this table. Notice we really aren't given any initial ones, so we really don't need the table. I'm just showing you where these numbers fit in the table. Because if you're kind of thinking, okay, how does this fit in the table? We don't know the initial concentrations. We really don't. We could write out the change row, but we really don't need it. We're given the equilibrium concentration of nitrogen and oxygen, and we're just asked the equilibrium concentration of the nitric oxide, or the NO. Okay. So we could write this out. And we know that this number is equal to the 4.1 times 10 to the minus 4. Okay, so we're good with that. We know the denominator pieces. Okay, so we can rearrange this. Let's solve for the NO2. So we move the denominators over to the other side. Okay, we take the square root, and then we have all the numbers for Kc into O2, so we can put those in. So the equilibrium constant here, and then there are two concentrations. So there's our concentration of nitric oxide, 3.6 times 10 to the minus 4. Okay. Any questions on this one? Yes.
Is there supposed to be a 2 in the NO2? Is there supposed to be 2?
It would be that case, like, so let's go ahead and do this. We have some initial concentration, so we would have minus X here, right? Minus X here, and plus 2X, right? And so it would be a plus 2X inside this thing, okay? And so if we were to try to find X, we'd have to take that into account. So we would say that this number equals 2X, okay? And then once we found X, we could see sort of how much we started with. We could kind of run it backwards and say, you know, let's say we started with 0 this. How much did we initially start with in the nitrogen and the oxygen? That would be a situation where we would have to know that this number equals 2X. But the way it is right now, yeah, this guy, I actually probably shouldn't have the 2 there. I should probably just have the concentration of NO at equilibrium, okay? And then the 2 shows up, the square shows up when it's in the reaction. So if y'all want to, in that little table, just scratch out that exponent because it doesn't really belong in the table. Okay, so in this case, we want to probably check our work. So this is another nice thing about some of these problems is we can confirm that the equilibrium concentrations that we calculated actually reproduce this number. So we calculated this number. Let's just do a check on our work. Let's put it into the equilibrium constant expression. So we had the original, the N2, and we had the O2. Now let's put in the NO and see if everything works out. So if we put that in, we square it, we divide by 0.036, and divide by 0089, we end up with 4.0 times 10 to the minus 4. And that's close. It's close enough, we'll call it a check. Okay, so with your little rounding errors, if you get something like that, you're comparing 4.0 times 10 to the minus 4 to 4.1 times 10 to the minus 4, you're good. That's good. A 10% error would be a change in 4 in that second decimal place, or that second significant figure. And so this is about a 2.5% error. It's 1/4 of 10%. Okay. I typically, for like Blackboard questions, will give you plus or minus 5%. So this would be within that 5%. How can I easily calculate 5% of this? Well, I just move this down, move it to the right. So 0.4 times 10 to the minus 4 would equal 10% of the original. Does that make sense? And then half of that would be 5%. So 0.2 times 10 to the minus 4 would equal 5%. So you're within 5% error on that. And so that's all I prepared. We're 5 minutes early. Happy Friday. You'll have a great day.